tutorial, we will be looking at a neural network with one input, one hidden, and one output. Enjoy. In the last series of tutorials, we did a neural network with one input layer and one output layer. In this tutorial, we're going to be creating a more complicated neural network that will be able to actually track more features by using a hidden layer. And so as you can see here, we have our inputs and we have our outputs. And in this example, this is from IamTrask again, so his link is down in the description below. He does it in 11 lines of code, but I'm going to be explaining it in a lot more detail so you can understand what's going on. You can see that the input here doesn't match our output. In our first example, it did, so we were able to get away with 0 hidden layers. Now we're going to have to use both of these hidden layers to figure out our output. The third input really doesn't have any bearing to the output, but it is just there just because we want a third input. Alright, so you can see if you know what computer science is or math or anything, and you've covered XOR, you can see that essentially the output is the XOR of the input. What that means is that they're the same, then it's 0. If they're different, if these two inputs are different, then the output is 1. And so what we're going to do is, like I said, we're going to use a hidden layer to make that happen. Alright, so it's the same black box from before, but now what does it contain? Boom. Don't freak out, actually. I'm going to split it up for y'all. So we have 3 inputs here. We have 4 elements in the hidden layer, and we have 1 output element right here. And so what we call that is 3 to 4, 4 to 1 synapse layer. This 3 to 4 converts these 3 inputs into 4 different sigmoid function inputs right here. As you can see, we take these inputs and we split them up between these 4 input layers. We have these weights A1, B1, and C1 for this right here, A2, B2, C2 for this neuron right here, A3, B3, and C3 for this neuron right here. And then all these outputs for these sigmoid functions go into another addition multiplication thing going on here, and that's going to be the dot product. Like I mentioned, this is the dot product of the synapses and the inputs right here that goes into another sigmoid that goes into the output. And so this looks very complicated, but what you should recognize is that it's just a more complicated version of this right here. We take these, we copy it 4 times, and then we essentially take that again and then copy it here. I know there's a 4th input here, but it works the same way. We use 3 addition gates instead of 2. So in here we use 2 addition gates to create a 3 addition gate input. We just add another addition gate and you have 4 inputs. And you can see the derivatives for those on the back are all the same. So for the addition gates, that's how it works. It's all the same right here. So that should make sense. If it doesn't, look back in my videos and hopefully it does. I'm hoping all of this makes sense and sticks. So, alright. We've forward propagated. So what are all these labels here? P11 is the value here between this addition and the sigmoid. It's the value of x1 times a1 plus x2 times b1 plus x3 times c1 here. P12 is x1 times a2 plus x2 times b2 plus x3 times c2 right here, and etc., etc. So you can follow that all the way through. All these labels are those values at that set points, and we need those to determine the derivatives that we're going to do in the backpropagation here. And so again, the error, we get an output, we have an expected output, and we have an actual output that we get from the function based off of those random synapses that we have. And so we take that error and we say that's DC or DP, or whatever the change that we want in that function, and we plug it in. And then now we just do the same thing that we did before, where there's the sigmoid function, here's the derivative. Again, we're getting that from this right here that we calculated previously, right here. This is the value right here that I'm copying. And the value that I'm plugging in for A is essentially this right here, this input right here. And did the same thing for the last neural net. And it's going to be P underscore 2 underscore 1 is that value that I plugged in for A. And here's that derivative right here. In the addition, it just takes that derivative and it gives it to all of these members right here, which you can see I just shortened that entire thing. I assigned that to DL underscore 2 underscore 1, and then I just set that because I didn't want to write that function out. Alright, and then that's the multiplication right there, and you know what multiplication does, right? The derivative at A underscore 2 is going to be the derivative here at this output times the derivative that we're getting from this plus sign. and then that's the same for all these values. And then from now on, what I'm going to do is I'm going to only focus on this one branch. And the reason is because things are going to get really messy if I do all of them at the same time. So with this one branch, the derivative at a2 is going to be this value right here times the derivative, that we're passing on from that addition sign. And so that's essentially dc right here times b, and b is this value right here. Right, and then so now we're just going to backpropagate again, and that's the derivative right here since we sent it through the sigmoid function. Again, I'm just simplifying it down into these functions right here. So I set that equal to d underscore p underscore 1 right here. You're going to have to really look at this and understand what's going on, because if you can truly understand what's going on here, you completely understand backpropagation for forward feed neural networks. And so, and like I said, you'll understand that you can do as many hidden layers as you want using these sorts of techniques. So this is a derivative right here. And then now I'm just going to backpropagate that again. This is dp11 here, which means that because to the addition just passes the derivative back on. dc equals dc here. So that's there. So the derivative at dA1 is equal to x1, the input, times the derivative that's passed on through the addition. And then there is no derivative at x1 because remember, that's a constant. x1's our input. So the derivative is 0, and the backpropagation stops there. And that's it. And so if you understood what craziness happened there, you understand backpropagation, and then you understand how forward feed neural networks work with hidden layers. It's really a beautiful thing, and take a look at that and really see if you understand what was going on there. And we're going to be doing code for this in the next tutorial. We're going to be using the modules that we learned from the previous tutorial when we started coding the neural network for the input and the output, just this simple neural network that we had here. So we're going to be using that code to essentially create the second neural network as well. Alright, well, hopefully this all made sense. If you have any questions, like always, please feel free to leave a comment in the section below, and I'll take a look at it and see if I can answer your questions. If not, then we're just going to start doing the code for the next tutorial. Thank you. Oh, and like I said, alright, so you use the Newton's method to update all of the weights. I didn't show all the work for this one, but if you understood how we did it for the first one, then you'll understand how to do it for this neural network. Alright.